Hello, gentle readers. Reading Foundations today, February 4, 2026. From a study with Ross Finlayson. Here in a review of sorts, an introduction to a library I've collected over some years. The previous video essay, these talks are about an hour long, was eventually titled Denser Tensors, with a brief recapitulation of what tensors are, descriptively primarily, and then as with regards to the relations of the relevance to other objects of the domain of discourse, of the language of mathematics, the mathematical universe. Vectors largely, and the Euclidean vis-a-vis other aspects of the geometry, and the singular aspects with regards to the origin and the horizon tensors, as thusly the notion that a tensor is as tensor does, it preserves its sort of analytical character of the products of tensors. Then with regards to relating that back directly to measurements of length and distance for the metric and norm, why then for all the usual accounts of mechanics that for Cauchy-Schwarz inequality, triangle inequality, or triangle rule, that there's for the product is the lengths of vectors is fits within a box. That thusly the account of denser tensors just kind of intends to, in a narrative of a stream of consciousness, to reach to not necessarily simplification, because it's so many complex, rather complicated things that get involved about what it is intended to formalize, but the overview of it, in a sense, vis-a-vis the thick of it, and with regards to the bogs and the fogs of these maps of the models of the things and our legends of them, these sorts of accounts. So today then, if that was denser tensors, the idea is kind of wider wavelets. And so waves and wavelets are very much having a formulaic approach with regards to periodic motion, and as well as being a model of change in an open system, because the general idea is that waves are as of water waves and pressure waves, matter waves, particles waves, and all these kinds of things. Then the wavelet is part of the account of well, how does the wavelet begin? How does the wavelet end? Vis-a-vis constructive and deconstructive interference and the crests and troughs and these other usual aspects of the slicing and the tomography of volume or an area, and resulting the idea that it results to a line somewhere or a point somewhere. Then that the wavelets are kind of as where that's at the boundaries. And so the analysis is often for bounded regions, for like Fourier analysis or many other matters of analysis, particularly Fourier analysis, but otherwise for any kind of systems of orthogonal functions that make transforms, to make for an analysis of those vis-a-vis infinite expressions, series, and how those relate, in this example, periodic functions, the Fourier series, to reconstructing the signals of things. So the wavelets are at the boundaries themselves, and kind of are these initial conditions in the behavior at the boundaries. Whether, for example, an impulse starts as say vertical or horizontal or 45 degrees is an account, whether it's rising by default, or whether it's divergent again from zero itself, or whether it's infinite to begin. These impulses for ideas like the radial basis function, which is basically kind of a bump on a line with area 1, or the ideas of Dirac's unit impulse function, which is a spike on the line with area 1. Then these kind of ideas of the wavelets intend to describe the kernels meaning kind of the seed from which the wave grows, and the ideas of then how those analytically are infinitesimals to waves. That wavelets are in a sense kind of infinitesimal waves, or that's the way to consider their approach. And so the waves and the wave analysis is very well explored for all such things like springs and pendulums and many matters of mechanics. Then that the wavelets are involved with all kinds of the ideas of how that begins and ends, from the little end of the infinite series, from the idea of bases functions which have expressions in the infinitary that result waves. So waves and wavelets. And then here, after the talk about Kelvin-Helmholtz, but for vortex rings and this kinds of things, is also spirals are really involved with the wavelet. It's kind of like the second most natural idea of like all the waves on the ocean beaches, every single shell is a spiral. And so spiral waves and wave spirals then are going to eventually make for models, meaning descriptive accounts of terms that have formal relations according to something like Herbrand semantics. Waves and wavelets and spirals and spiralets. Spiralons. For wave spirals and spiral waves, because both of those are sort of necessary to get an account of the unlinear that is a fuller complement, and so eventually going to be necessary to describe the real mathematics and the real physics of our real world. For it's very practically essential component in the correct sorts of derivations, which these days is so much made up of the empirical, i.e. outside the theory, the effects. So then I'll get started. This book is called Geophysical Signal Analysis, and it's from Anders A. Robinson and Sven Treitel. And so it's from the world of petrochemicals, essentially, or as of remote sensing as underground, so underground sensing. So some approaches to remote sensing are, for example, radar and sonar, or as after the waves and layered media, and the accounts of the medical imaging, besides more usual accounts like vision and these matters of parallax and Doppler and so on, for things about the geometric and the optical models of waves, and as for polarity and phase, and those being intended to describe what happens at the corners and the edges or going around the things, that then in sensing underground or ground sounding, there are notions of electroresistivity sensing, which is the idea of that different resistances and capacitances, but largely resistances of underground materials and bodies, enable one to lay out plots according to the worm finder is the usual idea of electrodes sunk into the ground and at various distances that, according to various simple enough formulas, that a survey makes for the ability to use very simple equipment to look underground 50 or 100 feet and look for water, basically. So if this is account largely, this geophysical signal analysis is a kind of a very then broader account of the ground sounding, and for things where, for example, they'll like drill holes in the ground and set up some dynamite, or have a vehicle with a large thumper attached and to just shake the ground, and then use the mechanics of echoes, waves, to find these things. That then there's also ground penetrating radar, another sort of account as of the ability to survey area, often for water or mineral deposits or voids or oil or gas or these sorts of accounts from the industry, and also just the practice of surveying. And so these are a lot of different things. So then what this book has is begins to describe this geophysical signal analysis. So from its title, you can infer that it's signal analysis, and so signals and information theory is considered a very, very abstract and general account of information at all. And it's often connected definitely and directly to definitions of entropy in information, but it's not necessarily so that signals and entropy are the same sort of thing. And that's from statistical inference as well, because there's kind of like the concrete and the causal in the signals and their construction and reconstruction vis-a-vis the statistical for these sorts of accounts. But it's got a lot going on. And so let's see, then here is, it says it's from 1980. So when studying the wavelets, this is kind of, it's not initial, and I'd like to, and I should study a bit more about wavelets and find out where ondes or ondelettes or waves or wavelets have that as kind of beginning, and that there are various accounts of what that would mean, whether it's considered only the analysis, like the Fourier style analysis for this wavelet style analysis, and the analyses, and then also for the infinitesimal analysis, what wavelets are as of that sort of account. So there's inner and outer and exterior ways of looking at these things, and then that they all still live in this one universe of mathematical objects as spiral waves and wave spirals is indubitable by definition, and these kinds of things. So it's got here in the picture at the front of this book, it says, "To our teacher Norbert Wiener." So this is for like Paley-Wiener, the ergodic, and the accounts of Markov, and the ergodicity, and as for Markov, and for oftentimes these days it's framed in terms of random variation and these kinds of things. But just like there are three large numbers, there are laws, and three continuous domains, and three limit theorems in probability theory, and three kinds of chance, and the standard account only has one, has that these functionals, or whatever they may be called, as after cybernetics in the account of Paley and Wiener as after Markov, then is and isn't independent other aspects of mathematics. So that's just a brief outline of that. The matters of Erdős's giant monster of independence in mathematics has that there are lots of things to do with the infinitary that are not actually resulting from the usual law of large numbers. There are others. And so it's matters of continuum analysis and having and doubling spaces, the quasi-invariant measure theory, and some other of these concepts in non-standard analysis that are still having real analytical character, as are considered here quite regularly, and is having an account of why for continuum analysis that this is a broader world of these sorts of accounts than is generally even understood at all. So Erdos then was a famous combinatoricist and number theorist mostly, vis-a-vis the concrete mathematics as well, for things like Szmeredi's theorem and arithmetic progressions and Ramsey theory, that each of these has branches, and they are singularities in a singularity theory, but branches in a multiplicity theory. So a bunch of these sorts of accounts, and including for things like Falting purity of Scholzi's perfectoids, which is not so, or anywhere you see almost everywhere, and that having to be shoehorned in instead of just saying everywhere. And for the accounts of measure, and the measure theoretic is for these halving and doubling spaces, and for the ubiquitous profusion of 2 and 1 over 2, and also 1 over pi for halving and doubling spaces and measures, and pi ratio spaces and measures. That these are accounts then as to why then getting into actually the development and derivation of these accounts is that we'd be looking for what is the non-classical or the non-standard aspects, kind of like Dirac's delta or notions of the impulse, which make for why wavelets kind of build their character, and then have an analysis about them. That then is those would be the kind of the signposts of where the asymptotic freedom of mathematical independence exists. So these are the kinds of things. A summary. The chapters begin. Preface 1 and preface chapter 1. A summary of seismic signal processing. 2. Causal feed-forward filters. 3. Minimum delay and causal feedback filters. 4. The stability of inverse filters. 5. All-pass filters. 6. Principles of least squares filtering. 7. The design of least squares digital wavelet filters. 8. The error and least squares filtering. 9. Stationary time series. 10. Predictive deconvolution of seismic traces. 11. Deconvolution for the elimination of ghost reflections and reverberations. The notion of resonances and waves is kind of for waves and wavelets as resonances and reverberations. 12. Deconvolution for the elimination, short period and long period, multiple reflections. So that kind of speaks to short period and long period, and minimum delay and maximum delay are kind of the corners, the initial and boundary conditions, if you will, loosely here, yet according to types and type theory, and the intentional and extensional in type theory, and for the guarantees of inference according to type, that the near field and far field, and as well about waves and their echoes, the stimulus and response of these things, is for flow and flux in the usual models of the fluid. That these help to reflect that in the convolutive is where both sides of these things are made accounted. So as for when there's a continuous reticulation of a smooth manifold to help express that it's continuum mechanics. And then when that wouldn't attenuate or dissipate, the classical accounts basically make for an inequality that marches off to infinity from the large end to the small end of the series, and making for an account relating to the geometric series, why analytical character, its value exists. Then these accounts of the near field and the far field and the mean field in the middle, and even things like metric and norm, or minimum delay and maximum delay, or short period and long period, the waves, is about the harmonics, and this is rather broad, yet it is so that then the notions of the completions of those are to be thorough, and it is given that usual accounts of them are partial to be tractable, and thus after being fungible. And so it's the sensibility that it's a continuum mechanics vis-a-vis any kind of aspects of the discrete, for the analog and discrete, that these are all part of this wide full dialectic, why then getting into a study of the analysis of waves and wavelets and spirals and spiralets, for example, whether that's just the initial outset of any path, vertical or horizontal here, in a diagram. That this chapter then is about deconvolution for the elimination, short period and long period multiple reflections. It has that trying to determine what was the noise, the signal in the noise, is an account for that. And then deconvolution is after convolution, is when it's possible to do that. It's kind of like in particle physics, there's discussion of normalizability, which is again just like how can we give it measure 1.0? And renormalizability, it's like, well, these things have been added together and cast apart and scattered and gathered again. Do they add back up? Is it renormalizable? It's like, well, it depends how they were denormalized to begin with, because it's just left out of the account. That's like, well, we forgot, we denormalized all this stuff from being continuous to be discrete in the first place. And so then trying to figure out how that goes back from being discrete to continuous again has that renormalization is only after an account of denormalization. And so somehow normalization in for standardization and normalization involves the real analytical character of what would be these non-standard accounts, but really just reflecting the giant atlas of independence. If Erdos has a giant monster of independence because they make contradictions, there's a giant atlas of independence, which somehow holds up all three of these worlds of the line reals, the field reals, and the signal reals. All in theory, which it must be. Chapter 13, seismic wave propagation in a layered system. So here a lot would be read from some of the other books here in the library about waves in layered media, and particularly, and Mogan's accounts, and the tensors and the accounts, and as of the waves, and those being basically planar on the chip, so kind of contrived very, very perfectly flat and thin, the layers, vis-a-vis like sand on the ocean floor underneath the ocean, or layers of stratified geography, or otherwise stratification. Then also that the ideas of turbulence theory and any of these boundaries get involved, because then turbulence theory it all starts with waves, wavelets and spiralets and spirals. It is what it is. Chapter 14, signal to noise ratio enhancement filters. So then this gets into the applied, and after something's fungible, making something tractable out of it. 15, migration of seismic data. 16, spectral estimation. So that's here that gets involved with light's special character, that's the model of the spectral and spectra largely. And then for diffraction and refraction, and also cleave, the crystallography, meaning the structure in the pyramidal, meaning the tetragonal, and vis-a-vis structure in the amorphous, and these kinds of things. That just kind of trailing off to help describe that spectroscopy and spectrometry and spectral estimates have that there's a great account for spectrum analysis or spectral analysis to make for why it's continuous, and to renormalize it again by understanding how it was denormalized to begin. That denormalized basically makes for, it means unnormalized, of course, but also then we could also read that as discrete normalized. These are kinds of the ideas. So for waves and wavelets, spirals and spiralets, for the giant monster of independence, a giant atlas of independence, then is for an account then, with that being kind of a high level view of the utter fundamentals of the things, that then when absorbing and beginning to walk or follow or sit through all the derivations of this great sort of account, and they're built with the usual account of integrals and sums and the tools of Fourier analysis, and then into the great account of this outlay of wavelet analysis from 1980, so quite some time ago in terms of since this field is new, that these are the sorts of accounts that from this book is something great to be taken from it. And so then each of these chapters kind of has an appendix, and the appendix give mathematical principles often. So, for example, the mathematical appendices read things like mathematical principles of classical lag window spectral analysis, mathematical principles of the maximum entropy method of spectral analysis, and then some programming algorithms for or a Fortran tool for ARMA. There's AR and MA and ARMA and these sorts of accounts of regression and modeling, these sorts of accounts. An appendix, Cauchy's solution to the wave equation, proofs of various relations for signal-to-noise ratio enhancement filter design, the minimum delay property of the reverberation spike train. So a spike would usually reflect on Dirac delta, the unit impulse function. And then here was mentioned that it's about resonances, echoes, and these sorts of accounts of then things that make for quantifying these terms and design and configuration of experiment. The reflection coefficient in terms of functions continuous at an interface. So this captures several ideas. The reflection coefficient, meaning usually according to angle and then absorption, what gets reflected and how to define what that is in terms of reflection, refraction, and diffraction, and refringence, those being kind of what happens in terms of perfect inelastic collisions, which just starts with like there is no reflection coefficient. That's just the model mechanics, the equal, opposite, opposite, or rest, motion, equal, opposite. Those that often I'll say that I'll say equal, opposite, opposite vis-a-vis equal, opposite, perfect inelastic collision, but it's also that both sides of those are like to so. So that then as soon as that begins to not be a perfect inelastic collision, then it's reflection. And then as soon as that kind of has any kind of moment arm, meaning like for Chladni functions, the divot, this refraction, but it's also a perfectly simple elementary function. And then diffraction is like, well, it's a fraction of two differences. It's a perfectly simple mathematical function that results describing this thing. But the actual behavior is like, well, the entire deconstructive account that arrives at mechanics and here is of waves and rays vis-a-vis matter and matter waves and bodies and objects in the usual sense. Energy in the entelechy. So the reflection coefficient in terms of functions continuous in an interface helps describe a couple of things because it's that striation, that grain of continuous functions, and whether that's invariant in conservation law or quasi-invariant in a continuity law, and then in terms of this quasi-invariant measure theory, the doubling and halving spaces. And so that's about then what functional analysis defines everything in terms of continuous functions and CINFT, the usual class of infinitely differentiable continuous functions. That here there are these other models of continuous domains implicit everywhere, just having equipped all of mathematics, which these things that otherwise it has to have. So these are usual accounts of a modern mathematics. A thoroughly modern mathematics. And more appendices. The inverse filter model, a study of a two-layer marine reverberation model. So in the aqueous, in the marine. The autocorrelation of a seismic trace. So autocorrelation is generally considered one of the nicest things in analysis to have because it's just a matter of balance, and it can be computed off of it. So auto-regression, autocorrelation, and these sorts of accounts are quick and numerical methods. And numerical methods are approximations. They have their modeling of their error bounds and these sorts of things always to take into account. They are nominally incomplete, of course, and imperfect. Yet they generally reflect on sensible, fungible, and particularly tractable means to get quick values. More appendices. The autocorrelation function of the autocorrelation function of a stationary time series. So basically, the classical line in the middle, how that builds. For Fourier analysis, it's like, well, how does Fourier analysis work? It's like, well, you start with 0, and then you add waves, and then, but according to periodic functions, with regular periodic functions of given fixed amplitudes. And then an infinite series of those results, whatever function there was, the signal. And so then an idea of a hat analysis is like, well, when you start with 0, it's like, no, you start with like a hat. And then that is regular over the course of the bounds, but then from the little end of the series, it just kind of flattens to 0. So like the infinity of those is a flat line, whereas the infinity of the Fourier style analysis is it's filled in area. It's a space filling curve it's a continuous function in a sense, but it's a space filling continuous function. And so a space filling non-crossing continuous functions are quite an involved thing, and that would be beyond the usual account of the standard. Just to not walk into having made for like something like Poincaré completion, who is a great geometer and considered in fact profound, that it's still then relatable in terms of like our standard linear curriculum as of a good 1980s, 1990s education in mathematics. The tuplets recursion, Toeplitz, tuplets. So the tuplets recursion, a recursion is for recurrence relations, and it makes for an analysis of what the recursion is. Just like Markov chains and so on get into the ergodicity, and ergodic is like what happens in the infinite as after a recursion in the behavior of these values over time. Then the tuplets recursion is otherwise an idea of that, whereas time is a sort of universal parameter. That's something we'll look at a bit and see what it says. Formulation of the filtering process in discrete and in continuous time. Inverse filtering in the frequency domain. So with regards to the frequency and time being the usual domains of an analysis, of Fourier analysis, then there's also about the continuous and discrete and trying to figure out the filtering process, as it were. Appendix 1.1, the normal move-out correction, or the normal move-out correction, figuring that the normal is offset, in a sense. The virial principle, perturbative, the hypothesis of small perturbations, the normal move-out method. These are accounts of when something is 0, and so it'd be like dividing by 0, just offset it and be like, well, how does it get to there from there? Kind of like small angle approximations, like, well, sine theta and theta, when they go to 0 over 0 equals 1. It's like, well, yes and no, because it's an indeterminate form, and one is based off the rotation, the other is based off the linear. And the fact that there is they're given as 1 over 1, being 0 over 0, is because the idea is like, well, sine curve is slope there is 1, and so we're just saying that also it would have to come from the box, like from our metric and norm, that box, to make this linearization 1 over 1. Otherwise, just a derivation usually hidden in all matters of stacks of derivations in physics that has these assumptions that go together to fall apart. And then is how our deconstructive account makes a stronger one built back together again. So then, that being just the outline, the survey of a summary of the chapter titles of this book, then let's find a brief passage to get some idea of the style of the authors. A substantial fraction of the globe's deposits of oil and gas is buried in subsurface rocks covered by water. Typically, a seismic source imparts a pulse of energy into the water just a few feet below the surface. Excuse me, I'll sneeze. This source pulse travels from the water into the rock formations below it, where it is split into a large number of waves, traveling along various paths determined by the material properties of the medium. Whenever such a wave encounters a change in acoustic impedance, which is a product of rock density and rock propagation velocity, a certain fraction of the incident wave is reflected upward. Seismic detectors situated near the water surface record the continual motion of the water under the impact of seismic waves impinging from below. This recording is performed digitally at a fixed sampling increment. The resultant set of discrete observations is called a marine seismic trace and constitutes a sample of a time series. And then in this development, it starts with minimal delay. It's like, well, if we can get minimal delay, we're looking for the first part of the response to come back. And there is yet this long tail and echo, and that's part of the idea of the classical that makes it hard to set up energy and configuration experiment for long duration experiments, is that there's no time to do that. And so the idea of minimum delay is greatly employed here in Robinson and Treitel's accounts. A minimum delay wavelet is defined as a wavelet with its energy concentrated near its arrival time, as opposed to a mixed delay wavelet, which is defined as a wavelet with its energy distributed away from its arrival time. The concept of maximum delay is defined for finite length wavelets. Namely, the maximum delay wavelet is the time reverse of a finite length minimum delay wavelet. And then they define a first order causal feedback filter and its stability related to the property of minimum delay. So that's like Doppler. That's like a lot of accounts of shortest distances and smallest angles, or a parallax in Doppler. Then for these sorts of accounts that you can build the layers under that in terms of these wavelets, and they add back up. Waves in layered media. Now, time series is mentioned, and then for the filter is and the like filter banks, the idea of this being hardware in the digital usually that makes it possible to reconstruct from these events or samples or signals. Is for something like, as the authors put it, memory, which is like how far back can we keep track of what we've been seeing, or how long can we wait and know what we were waiting for, and anticipation. And that's nice to introduce for the whole convolutive setting, which is kind of like, well, from this one perspective of the setting, it just goes out and we've made sure bounds either sides, and then the convolutive is like between the bounds. It's both ways between the bounds, and so memory and anticipation are accounts then for uncertainty and expectations, kind of loosely, technically, in a type theoretic approach, qualifying that to have it so that memory and anticipation are introduced as the relevant terms about basically that would be the training in today's modern accounts of neural net models and these other sort of feedback-directed optimizations, and memory, the current working memory, in a sense. It is worth noting that models of both discrete time systems and continuous time systems should take into account uncertainties in the amplitudes of the variables. A signal, whether it be a train of pulses or a function of continuous time, always has imperfections in its amplitude, and these make its precise measurement uncertain, Moreover, a signal that appears as a sequence of numbers always has an uncertainty in magnitude, the degree of this uncertainty being at least equal to 1 unit of measurement. And so this is where basically then if you have a reference model for a sounding, like the ocean floor was already kind of mapped out, then if you're looking for something like a new volcano or a new sunken ship or something like that, it is possible to make an account of reflecting that back off the floor instead of that. Otherwise, this is a way to reduce this sorts of accounts of otherwise that would be lost in the floor and these kinds of things. Reason for exploring discrete time systems instead of continuous time systems is twofold. The authors note, we may present the basic ideas in more simple mathematical terms, and two, we may develop programs for a digital computer in a universal computer language such as Fortran to carry out the mathematical operations. And also it's an account of the finite and infinite and everything, making things classical at all. So yeah, the finite and infinite and normalization of these things is very much for an account of the classical. And then here it's particularly we have tools for continuum analysis of time series data, and if those were to get particularly fine, until we lose the difference there, that there's these kind of three different floors of attenuation about the smooth and grainy and continuum analysis and for finite element analysis. So about continuum mechanics, and here particularly about the real analytical character of these sorts of things. So I've been leafing through this, kind of browsing around in this book for a while, and I'm going to set it here next to this Horace Lamb's Hydrodynamics, which is an important account of the field of hydrostatics, particularly besides hydrodynamics, and Odo Richardson's The Electron Theory of Matter, which is much involved also with the accounts of after the electricians of the 19th century, the fields of electricity and electromagnetism. So thusly, it's kind of it's considered potentialistic theory, because some of histories is kind of like, according to our estimation, this is where it's at in measurements, and then some of potentials is like, and this is everything that's pending. And so the potentialistic theory is a greater, wider account, and it's just so that the theory of harmonic functions as the theory of potentials is just incomplete, because they're after things like Chladni functions, which are ways to beat the membrane of a drum from different angles and as from different impulses to show that the resonances collect in various patterns. Besides that, classically, it's like a model of the vibrating or plucked string, whether it's plucked to the side or whether it's entirely vertical. How that can deform the string, because that would only happen exactly in the middle of a string. Ideally, that all these different notions of the impulses and what can then make reverberations and echoes and resonances from these wavelets to arrive at these not exactly ideal, like perfect inelastic collisions, as just was mentioned. The unlinear, that worlds turn. And a true potentialistic theory, to be complete, is more than merely partial, say. All in theory. The Metaphysics of Virtual Reality. A book by Michael Heim, H-E-I-M. New York, Oxford University Press. He's also written books that says Translations of Heidegger, The Medical Physical Foundations, and Electric Language, a philosophical study of word processing. 1993. 1993 was a pretty good year for virtual reality. VRML, Vermal, that was becoming a thing. It was the internet was about to break on the world in the next year or so. If virtual reality were just another technology, you would not have heard so much about it. However, it is a technology that can be applied to every human activity and can be used to mediate in every human transaction. No, that's just the realm of thought, and then the realm of fabrication and dissimulation and illusion, you know. So virtual reality kind of came up like about the same time as nanotechnology. So like in 1989 or to 1991, some things that were being studied with regards to things like space exploration for whatever reason included nanotechnology, which is again kind of like it's magical. What can you do with nanotechnology? Well, according to Eric Drexel at MIT, you can do anything. You can make self-assembling nanomachines and these sorts of things. The nano assembler, and so that has almost as much hype associated with it as quantum computing, right? And so virtual reality then is also this idea. It's like, well, it's simulation. It's like, well, should we try and make a black hole in the lab? It's like maybe we should simulate it first, you know. And then with regards to virtual reality is with regards to the presence in avatars and these kinds of things and expression and just another medium is a different sort of thing. So that's what he says about the accounts of metaphysics. So that was kind of from, this introduction was written by Myron Kruger. In this book, Michael Heim points out that virtual reality is the culmination of a process that's been going on for some time in technology, for even longer in Western thought. So about Turing tests and the idea that, for example, robots can, or mechanical inference can be indistinguishable from a human in terms of capabilities and then also personality. Then there's also the idea of like, what about a Turing simulacrum? Can you deepfake somebody entirely accurately? The answer usually being no. And then for questions of free will and stuff like that. That otherwise virtual reality and the notion of perception and sense within it, and matters of perspective and projection, are that it is it's essentially has an aspect of the discontinuous. It still is an overall continuous realm. So if we're living in a simulation, nobody's ever going to know. But lots of accounts of inference and with regards to their expectations and beliefs, if those are broken at all, then it was like, well, I guess that was the wrong matrix or something like that. And so are we living in the matrix? Only in the sense of that there's it's an infinity, it's a continuum, and it might be all zeros and ones up there, but it's all true and false here. And it's continuous is the usual idea. And causal, the laws are the same everywhere. That still gives a great wide realm of potential and possibility, and almost what would be perceived as miracle every day. The nonlinear free association format of hypertext has been incorporated into multimedia, the most recent revolution. In this new technology, the black and white, static, symbolic, sensory deprivation world of the intellect has begun to yield to multisensory modes of presentation. The awkward juxtaposition of pictures and words that exist in print gives way to a new form of expression in which illustrations dominate. By totally immersing the consumer in illustration, virtual reality is the momentary culmination of this evolution. So besides like the feuilletons, the idea is just like it's sensory input meant to distract or garner the attention, the interest and the attention. The idea that the guy's living in a box is kind of like what's that the music video, Soundgarden's "Blow Up the Outside World" or something like that. Whereas after an account of the purported idea of rehabilitating the criminals in A Clockwork Orange and giving them sensory stimulus, basically as an opposite of sensory deprivation, but the overload instead, that it didn't really work out how such operant conditioners figured. Oh, there's some post-it notes in here. The previous owner of this book has written some post-it notes. VR remains a focal issue of interdisciplinary and lay debates. The reverse of what is true historically, that is technology driven by... Things change even before we realize what has been happening to us. Again, in the preface, widespread use of automobiles, knowledge in a scientific sense can lag only slightly behind this world transformation because knowledge becomes transformed in the process. The holistic background, a world is the basic reality underlying our knowledge and awareness. Ontology, the study of the being, is the effort to develop a peripheral vision by which we perceive and articulate the hidden background of beings, the world or context in which they become real and meaningful. So, talks about, there's like essays on Heidegger and McLuhan and sorts of accounts. The media is the message. Given the right motor, the Leibnizian symbolic logic is developed later by George Boole, Bertrand Russell, and Alfred North Whitehead, then applied to electronic switching circuitry by Shannon, can function at the speed of thought. Here we have, of course, a better than quasi-modal logic to begin. I mean, that's has flown right under the bridge. Centuries later, John von Neumann of Neumann applied a version of Leibniz's binary logic when building the first computers at Princeton. Well, yeah, what of it? Leibniz's modern logic, Aristotle's logic traditionally, Leibniz's electric language, and so that's an approach by our metaphor to a strong metonymy of a universal language of Leibniz, and then for a Comenius language of truths and truisms. Hyperspace, cyberspace. Like the fictional hyperspace, cyberspace unsettles the felt logical tracking of the human mind, or it establishes for its surroundings and considerations to understand that it really is a maze of twisty tunnels, all alike. You know, as that being the kind of the initial line of Zork, a kind of a freeform textual adventure which transformed via multimedia and interactivity. The whole other account of, after Choose Your Own Adventure, books and the world of books and the realm of thought and the literary. And then hyperspace is actually just is more usually an account of the pan-dimensional and the polydimensional, not so much necessarily the disconnected, vis-a-vis the way things can be connected, about connections and action. So yeah, this is a theoretical account of a lot of matters for these things. Looks like it's time again for philosophy. Useful vocabulary for the metaphysics of virtual reality. Aesthetics, agents, altered states. Analytic, synthetic, artificial life, artificial reality, augmented reality. Alternate world syndrome, alternate world disorder. Bandwidth. Binocular omni-orientational monitors. CAD-CAM, computer-aided design, computer-aided manufacturing. CompuServe, cyber. Cyber, a prefix found throughout the literature of VR. The root reference is to cybernetics, the science of self-regulating systems. But the reference has expanded to become a name for mainframe computers and now connotes the human involvement with computers. For instance, the primary human body becomes a cyber body when appearing in the cyberspace of a virtual environment, or the avatar, and these kinds of things. So this book from 1993 or so is foretells the field, you know. Old wrapped as new so many times that people living in a simulation don't even know that that's running in a simulation. Concise Encyclopedia of Atomic Energy, edited by Frank Gaynor, Gaynor. Then it has a comment, E equals MC squared. E equals MC squared, Concise Encyclopedia of Atomic Energy. The purpose of this book is to present a comprehensive collection of brief explanations and definitions of concepts and terms in the field of nuclear physics and atomic energy to the scholar, researcher, teacher, librarian, student, and intelligent layman. There are individual entries for every element indicating chemical symbol, group of the periodic table, name of discoverer, date of discovery, atomic number, atomic weight, melting point, boiling point, specific gravity, stable isotopes, radioisotopes. Brief descriptions of the best known types of nuclear reactions are given. There's an entry for every member of the known radioactive families, including symbol, atomic number, mass number, parent isotope, daughter isotope, type of radiation, half-life. A great many brief and concise descriptions of subjects such as nuclear fission, tracer technique, atomic bombs, H-bomb, etc., etc. Further, electrical, magnetic, chemical, and physical units, important nuclear research laboratories, power plants, installations, etc. Also, thumbnail biographical sketches of outstanding nuclear physicists and chemists. In itself, a pocket who's who of atomic science. Who's who was an old social register. And I'm not sure by the time you got invited to who's who, it's like you're invited to who's who, send money. And whether you did or didn't send money, I'm pretty sure that who's who still keeps track of everybody who was ever in who's who. That's their business. Over 2,000 entries, numerous charts, tables, and illustrations. Another supplementary picture of the book, listing of the German equivalents for a great many of the terms defined. An ex libris here. Tinny, T-I-N-N-E-Y. Concise Encyclopedia of Atomic Energy from the Philosophical Library of New York. So that's also where Einstein's Out of My Later Years was as the publisher. Published in 1950. About the intra-atomic and interatomic. It's a dictionary. Ab-Henry, ab-farad, ab-mo, ab-ohm. So they have ohms and then reverse ohms, or MHOs, mos, ab-mos and ab-ohms, ab-henrys and ab-farads, so usual magnetic units of farads, or henrys, and usual or inductance and capacitance of farads. Ab-coulombs, quantity of electricity. 1 ab-coulomb is defined as the quantity of electricity which passes any given point of an electrical circuit in 1 second when the current is 1 ab-ampere. So it's defined by amperes up here then, I suppose, too. The electromagnetic unit of current. So it's not, it's never static, but, you know, it's as of a statics. Current in this CGS centimeters, grams, seconds system. These are not the SI units, even today. 1 ab-ampere is defined as the current which produces a magnetic intensity of 2 pi oersteds at the center of a circuit in a one-turn circular conductor of a radius of 1 centimeter in a vacuum. So all this stuff to do with waves and wavelets and spirals and spiralets is a maelstrom about all this stuff, which is just smooth in the middle. 1 ab-ampere equals 10 absolute amperes. And then so absolute edge, absolute absorption factor, ab-volts. So much like there's abceleration to do with acceleration, or absement to do with acceleration. You got these ab units all over this nuclear theory. So there's a lot of the practical implied by this that doesn't get much press usually. I mean, the press is usually like, it's like we're G2ing our muon just like everybody else, and it's like, what exactly do you mean by a muon? You know, in these things. Let's see what it says muon is here briefly. Oh, potential, of course, potential barrier, potential vault. The electrostatic energy. Here's a table. Nuclear neutron excess n minus z as a function of the atomic number z for the known nuclei. So this is kind of like for the nucleonics instead of the hadronics defining what nuclear things are. M. Microbar, microcurie, micron, milliammeter, millibar, millicurie, millican, proper name, millimicron, moderation of neutrons, moderator, mole, the gram molecule, the gram atom and the gram molecule, molar, mole, molecular, molybdenum, I'll often say molybdenum, Demon. Either way, it's only spelled in as always. There's only one of those. It's not like mos and ohms, which are kind of reverse. That's their portmanteau is putting them back together that way. No entry for muon. So this is of a time. This is a great sort of count. Rydberg constants. Reactor. Does this book glow in the dark? Everything glows in the dark. Let's see. Well, gentle readers, we've reached about the hour. We're about a third of the way through this book. There's about 30, 35 more boxes of books. So I'll wish you a good day in this discussion of wider wavelets, or that being an introductory sort of term to engage the brain in this account of continuum mechanics. It's a continuum mechanics.